Yeah, today we're going to talk about reporting results of statistical tests. The motivation for this is this. Sometimes different people, different people, managers may disagree on what alpha they should choose, the significance level. Should I pick 5%, you pick 3%, someone else may pick 1%, because it's basically based on how serious the type 1 error is. So instead of telling someone the statistical test should be rejected or not rejected because you base that on a specific alpha value, you just give them the p-value. This is the p-value we're going to talk about today, and they decide. So if the p-value is less than the alpha that seems reasonable, then they reject the hypothesis, and if it's not, they don't reject it. So that's basically what alpha p-value is. It's a value that corresponds, it's an area under the standard normal distribution that corresponds to the test statistic. And so in this case we just compare alpha and another probability, which is the p-value. So that's why the definition here says the p-value for a test of hypothesis is the smallest value of alpha for which the null hypothesis is rejected. So you reject for all p-value above that. The statistical result or the statistical results are called significant. Okay. So the p-value is called the observed significance level. It is also called, sometimes it's defined as the probability when H0 is true of obtaining a value of the test statistic, a value of Z, as extreme or more extreme than the actual sample value that supports the alternative. I think the best way to understand it is through a series of examples. So I want to give you an example for each one of upper tail, lower tail, and two-tail tests. So how do we compute the p-value in each case? So if I have an upper tail test, and I have basically I'm testing H, whether mu or theta greater than theta 0 versus theta anything else. So theta can be p or mu in this case. And I find out my test statistic is 1.76. Then how would I compute my p-value? Here is what it is. So we go here. I'm on the first graph here. So this is my value. This is my test statistic. It's 1.76. And then so I want to compute this area. Okay, this is not the critical value. So say if my alpha is 5%, my critical value would be here, and this would be 1.645. But this is my test statistic value. So I want to find this area. So I go to the table, the Z table. I find this area. So I go here into the Z table. I go 1.7, if you remember, 0.06. And go down here, I find this area, and that would be this probability. So I take whatever that area I find, I take 0.5 minus this area, and that would give me, because that would give me this area in the upper tail, 0.0392. Okay, so please go pause the video, go to your Z table, check to make sure that's what you have, and come back, and that's called the p-value. So this is my p-value. Okay, so again, now if my alpha is 5%, I would be down here, and then this is less than 5%, I reject. If my alpha is 1%, it's going to be my alpha would be up there, and this would be larger, so I do not reject. So it depends. I'm just comparing areas to areas in this case. Okay. The same thing goes for if I have a lower tail test. So my theta equal theta 0, and the alternative is theta less than theta 0. So my Z would be negative in this case, since I'm in the lower tail. It's negative 1.86. So how would I find the p-value? So again, I go to my graph. Best thing is the graph. I put down the value, which is negative 1.86. 0.86, and now I want to find this area. This is what my p-value is. So in this case, this is my p-value. So to find this area, first I need to find this area A here, and I can find that in the Z table. Again, I go to the Z table, I go to 1.8.06, and I find that area there. By symmetry, that would be the area here, but it's the same as there. So this whole area is 0.5 minus A should give me the 0.0314, and that's my p-value. So if I pick my alpha to be 1%, then I don't reject. If somebody else picked their value as 4%, they would reject. Okay. Remember, the p-value is positive even though the z is negative, because p-values are probabilities. They are areas under the normal curve. Okay. Let's see what happens if I have a two-tailed test. Again, whether this is mu or p, and say my z is 1.76 now. I'm saying here the p-value is twice what I had up there. Let's see why in the graph. So now I have a two-tailed test. That means this is my z here, 1.76, and I take the negative part of it. So because I have a two-tailed test, what I have here in this tail would be half the p-value, and so the other half would be compared with the other value. So this value would be compared by alpha over 2, and therefore whatever area I have here, I just multiply it by 2. So that's simple. So if you have a two-tailed test, double the value you find from the upper tail, and that gives you the p-value, so you can still compare p-value with alpha instead of comparing half p-value with half alpha. Alright, and so that's how you compute the p-value in each case. And now, after calculating the p-value, you reject H0 if the p-value is, typically that's what we do. If the p-value is less than 0.05, we reject it. If it's more than 0.05, we do not reject. If the p-value between 0.5 and 10, then most of us would fail to reject because that's the default value. But in general, it depends on one's tolerance of error. So what did you pre-select? Because alpha should be selected before you start the problem, before you start even collecting data, because it's an indication of your assessment of how significant the type 1 error is. So if you find, and then your answer would not be biased that way. Okay. I'm gonna stop here for this lecture, and thank you.